Good afternoon, everyone. So today I will be presenting about how we're planning sustainable bio-inspired printed infrastructure for erosion control. So this work is being conducted with my team. So now there's a postdoc, a master, and a PhD student. So just to recall the context, I mean, we know that erosion control has significant effect and also large cost. So I think the insurance company are aware of it. And then as engineer, I think we need to start thinking about solution because we know that the very impactful event are increasing. Like we know that the sea level is rising and we have also higher storm rate. So if we look closer at where I'm from, the St. Lawrence River, there's also very visible sign of erosion at some area of the river. So different organizations are looking at solutions. So there's a Nature Conservation Canada, that is one organization that is looking at preserving the habitat. And then there's also the Port Authority that is also having some responsibility towards the change in the shoreline. So if we look closer at it, so let's say we take the province of Quebec where I am from. So there's 35 ports. And then there's 3,700 navigable ways. And then there's a lot of sediment that is being generated each year. So the idea is to see, can we use this sediment and try to form them in something that can be useful to prevent erosion. And then if we look worldwide, I mean, if we look at key countries, we see that the amount of sediment that needs to be removed for the navigable way is very high. So, and then when we look at the cement industry, we can be building infrastructure, but we have to be mindful of the CO2 emission because we want to find sustainable solution. I think just this weekend I was reviewing the local news, and then I see that there's warning about building seawalls because in the long term that doesn't allow the beach to have its own cycle of sediment. So here, there's a possibility for 3D printing concrete to design local solutions. So this is what we are looking at the moment. So basically, there's ongoing discussion with the local stakeholder, and there's a representative to speak to the First Nation because some of the ground is also protected by the First Nation. There's an ongoing review of the IPCC recommendation to really identify the solution, and then there's 3D printing concrete solutions that are available, but then we need to see how can we adapt them with low carbon printable material. And then we're also looking at, I think there's two lines, like a reference mix without sediment, that we are more sure of the durability properties, and then we are also looking into a mixture with dredge sediment that can allow to be also using local materials. And then for sure there will be a durability test campaign. So just to recall what this large intergovernmental panel on climate change is saying is that coastal erosion is actually a complex situation. Like there's a link to global warming, but it's not the only cause. Like for example, on the St. Lawrence River, there's also an increase in the navigation. So that's also direct cause, but that's 50% of the explanation in the erosion that is happening. And then we know sea level rise is something that is ongoing. And then they are finding out that like it's higher when there's no physical barrier to prevent the removal of sediment, but at the same time, we have to be mindful of not necessarily building a wall. So, and then when we look at more the impact, adaptation, and vulnerability, so coral reef, we know they are also at risk of decline due to erosion, and then the impact are higher when there's a coastal development that prevent habitat formation and when they disrupt the sediment cycle. So, and we know that the natural ecosystem, they allow to reduce the wave energy. So there's all of that we have to keep in mind. So we also need to keep some space for the ecosystem. So when we look at the concrete solutions. So we see that there's printed artificial reefs that are being designed. I think so. I mean, that's something that we can do with 3D printing that we couldn't necessarily do before. And for sure, there's also other way to go about it. Like we could do also a more hybrid type of manufacturing, but that's a solution that is 3D printed. And we see that usually they work with a concrete that is resistant to chemical attack, and they are mainly justified in terms of promotion of the aquatic biodiversity. And we see in this case that there's a lot of infrastructure to place them at the right location. And when we discuss with different ports, that infrastructure is not always available. We see that to have access to a large boat like that, you would need a large port. And then let's look at another solution. So this is being done in Australia. So they are making, this is definitely, in this case, we looked at this probably in a formwork that is designed to do a seawall. So supposedly with this structure, there's a rapid increase in the species over 1 to 2 years. It improves water quality, and there's up to 20 habitat types. So that's quite inspiring. And then closer in the US, we've seen these concrete tide pools. So they are prefabricated. They are suitable when we have more rocky shores, and they are more to promote also the diversity. But I think the challenge when we do the review is there's no clear guideline on the type of structure to prevent erosion control. And then when erosion control is the prime argument for doing a new structure, then there's a need for more research. So we see in this case that there was a study of the fluid mechanics around, it looks like a printed solution. And then in this case, we see that it also allowed to attenuate the waves underwater. So when trying to design a new concrete mixture, I think what we can know from a site is the chlorine concentration, and if it's fresh or salt water. We know if there's presence of freeze or no freezing. I think what there's less data about is in case of presence of ice. There's few sites where we really know what is the stress from the push of the ice. So this is, I would say, current unknown. There's, for example, in Canada, there's just the Confederation Bridge that is in Prince Edward Island, where we have data on that. And then also the fatigue stress from the wave. There's not clear guidelines on how it impacts the structure. So I think this is something where we need to think of experiment to get the proper information or check if there's historical report. Now let's see how we're looking at the low carbon reference mixture. I think we're very inspired by the LC3, so it's a mixture of cement, limestone, metakaolin, and calcine clays. So, well, there's different ways to look at it. So, and then we have a set of criteria. So we have one with the global warming potential, like in terms of kilograms CO2 equivalent per kilogram of concrete. And then from the 3D printing literature, we know that we have a criteria on the slump, on the thixotropy, and the compressive strength. And then we do a rather iterative design, and we are using the optimal design of experiment to try to get as much information from a limited amount of experiments. And then we are doing training, or we're combining experimental method and some machine learning algorithm to go faster. And then, I mean, the work is ongoing. And the other line of work that we're doing is to evaluate the reactivity of the local sediment. So we collected sediment on the shore where there's plant development. So that's also in a zone with high erosion. And then what we are doing is a set of reactivity tests where we look at the raw material and then we calcine it from 600 to 1000 degrees Celsius, and we did the reactivity test to see do we need to calcine it, or is the raw material good enough? How much can we replace cement with it? And so far, our results are very promising because it looks like the raw material that is not calcined is performing better than the one calcined at 1000 degrees. So then, and even there's not a very big difference between the raw material and those that is calcined at 600 degrees Celsius. So for that reason, it's very likely that we'll go with the raw material, and then we're trying to find out what is the percentage replacement that we can do. And eventually, we will try to also include our printability requirement to find the proper printability mixtures. So to conclude, I think we know that erosion control is a pressure ring issue, and then there's no clear guidelines yet on how to design a structure, what's the right concrete mixture. We know that we need to have a concrete that will be low carbon if we want to be coherent with this discussion about adaptation to climate change. Local sediment can allow us to use the local resources and reduce the amount of cement in the mixture. And then there's potential application for 3D printing of concrete. We can do artificial reef that could have the dual role of promoting biodiversity and at the same time accumulating the energy from the waves. So this is ongoing. So, and I would be curious to know if others are doing experiment in that line. So, and then I would like to acknowledge there's a Réseau Québec Maritime, which is a network that is looking at the attenuation of the impact of navigation. So they've been supporting us. Yeah, thank you.
Thank you. Thank you. Good afternoon, everyone. My name is Mehdi Khanzadeh. I'm an assistant professor from Temple University. So today I'm going to basically discuss the application of cellulose nanomaterials in 3D printed composite system for mainly architectural applications. I would like to thank you, my student Abdullah, Garrett, and Nathaniel. They're interested in work on this. So here's the motivation for our study. As we know, 3D printing is getting more popular for different applications, but the system we are using for 3D printing, low water binder systems, right? A lot of cement. It's not cost effective. It's not sustainable considering the initiative we have currently. So we were thinking to use this cellulose nanomaterial, which are a green material, in the 3D printed system to improve both fresh properties or printability and also the mechanical performance, which I'm going to discuss. And the other part of this study, kind of novelty application of this material in alkali activated binders. So objectives, as I said, developing the mix design using these cellulose nanomaterials and looking at the impact on the printability and harden properties. And also our collaborator from University of Wisconsin-Madison, they're basically using this as the input information from our experiments for techno-economic analysis to see if this is feasible or not. So the background about the cellulose nanomaterials, mainly we use the CNCs or cellulose nanocrystals in this study. Also, some other people use the CNFs, the cellulose nano fibers in the concrete, mainly in the mold concrete, traditional concrete. So these are crystalline part of the cellulose, typically extracted through the hydrolysis process using acids. The size, as you can see on the let me see. Here on the upper right side, the width around few nanometer, the length around 50 to maybe 100 to 100 nanometer. So the large benefit from this use of the CNCs are they are renewable materials, they are biodegradable, they are sustainable. Currently, even they've been used in the cosmetic industry or in food industry. So they are very safe, and we have them in high quantity in the nature. So these are really great benefits from use of these materials. So here are research scopes. I'm going to discuss how we design the mixes, the impact on the fresh properties, and then performance. So as we know, there are some challenges for developing the mix design for 3D printing compared to traditional concrete, obviously. Considering our limited experience with this. So for extrudability and printability of these systems, we consider this parameters, basically the extrusion consistency. We use the extrusion pressure. So as you can see at the top right side, we use a similar system as Narayan discussed. Basically this syringe system, by changing the RAM or displacing the RAM, we can look at the pressure, how it changes over the print time. The splitting and tearing, obviously you are familiar with this, right? This is not a acceptable system. And regarding the buildability, we looked at how many layers we can stack. Since we were interested to print 2-inch by 2-inch geometry, so we printed around 11 layers. And if we didn't see extensive deformation, then that was acceptable for us. And also in some system, we saw excessive water leak from the nozzle due to the separation of the material. So that wasn't the printable system either. So based on those criteria, we developed these 8 different mixes. At the top table, you can see the OPC mixes, controlled without CNC, and then different percentage of the CNC by volume of the cementitious material. At the bottom, you see the alkali activated system, again, control and different CNC proportions. In case of the alkali activated binder, we use the mix of flash, classic flash, and slag. So 70% flash and 30% slag. Again, I'm going to discuss how we come up with that number. The CNC were in aqueous suspension, around 11% solids. And for the activator, we use the combination of a sodium hydroxide and sodium silicate. This is our printing setup. At the left side, you see the printer. We designed the printer in a way that we have a plug-in system. Basically, we can plug off easily, load the material, consolidate it, and put it back. So this gives us a lot of flexibility in the open time, right? So it extends our open time. So here you see the example of the printing. As I said, 2 by 2 by 7 inch. So we can cure them, we can cut them for compression or flexural experiment. So after printing, and regarding the pattern of printing, we use this, basically the outer or perimeter layers is more straight line. The infill is more zigzag. And the main reason for this basically we got better dimensional stability from this pattern. So after printing, we cure the sample, the OPC system, 28 days inside the water or the calcium hydroxide solution. For the alkali activated system, we adapted 2 different types of curing. The first method, we seal cure them for 28 days. The other method, we heat cure them at 60 C for 7 days. Regarding the basically fresh properties, this is the what I'm showing at the right side here. Here, the x-axis is the CNC dosage, the y-axis is the required liquid to solid ratio to be printable. So as you can see, for alkali activated system, we need more liquid to binder ratio to be printable, but for OPC lower. But something we noticed, after 1% CNC use, we see this higher exponential increase in the case of the OPC, and we're seeing that's the critical point to reach that agglomeration and aggregation of the CNC and OPC system. Regarding the pressure, I mentioned to look at the consistency. So this is the example you are seeing here. We have alkali activated without CNC, with CNC. So the use of the CNC lowers the pressure a lot, and this works as a viscosity modifying agent as well as the high range water reducer in the alkali activated systems. Here's how we developed the alkali activated mix design. So you see the combination of the basically activator as well as the change in the composition of the binder. So we looked at which portion is printable with retarder, and where's the optimum mix. So you can see that here. And if we look at this by that pressure graphs, so you see non-printable system at the left side here, right? So this very high pressure requirement, and you have this hard time to basically extrude this through. And at the right side, these are the optimal mixes I mentioned. Regarding the mechanical performance, by inclusion of the CNC, this is the modulus of the rupture versus the CNC dosage. So up to a certain percentage, again, we see an increase in the flexural strength or the MOR of this system by use of the CNC. By using the heat cured for the alkali activated, we see much more improvement, the black dots you are noticing here. The other point here is we have to notice that the reduction at that higher percentage is part of it because of we are using a higher water binder system. So that's basically reducing the mechanical performance. This is the compressive strength versus the flex or MR, right? And we compare with the ACI equation. So you can see the heat-cured alkali activated is very ductile system, even if it's performed as a high-performance concrete. And that's a CNF mix we tested. Even CNF mix with a 0.1%, it showed very promising result, 30 to 40% increase in the modulus of rupture. We looked at the porosity of this system. There's a strong linear relationship between the compressive and porosity. The electrical resistivity, we saw some abnormalities, and we think this is mainly due to the leaching of the alkalis from the reacted unreacted phases in the system. So that's why we are seeing a higher electrical resistivity for alkali activated versus the OPC. The other interesting observation we had, the internal curing effect from the CNCs. So when we are looking at the bound water over the depths of the samples, we are noticing in OPC system there's a increase in the degree of hydration. So this can be really helpful in 3D printed system when we have lower permeability, right? The external curing effect is limited, or the depth is limited. So this is an interesting observation we had. But in case of the alkali activity, there's no impact on the reaction, which was understandable. I'm going to skip this one. We looked at the SEM images after the flexural experiment. So at the left side, alkali activated seal cure, right side, alkali activated heat cure. So you see a lot of cracking in case of the seal cure, which makes sense, right? We have low strength for the seal cure one. And the main reason we observe here is due to the heat curing, we get higher dissolution of the flash particle as well as the slag particles, and we get more cohesive and uniform structure. So even unreacted flashes or slags are embedded inside that matrix, so that helps to improve the strength of the system. This is an observation again from IDA Explorer, the main product. So at the upper picture, you can see a lot of unreacted flashes from in seal cure versus the heat cure, which is minimal. So as I said, we introduced some of this as a for input as a for techno-economic analysis. So I'm going to skip this one due to the time limit. So these are the conclusion. CNC can help to improve the printability of our alkali activated and OPC system, works as a VMA, and also CNC improves the mechanical performance and internal curing effect, and finally the sustainability part, right? It can really work as a sustainable system. So with that, I thank you for your attention.
Thank you very much. We have time for one question. I actually have I have a question. So when you use the CNCs, you're getting an improved extrusion, right?
Yes.
And then does that have the similar effect on buildability?
Since it acts as a VMA, I would say yes. So it's kind of retaining the shape, helps with the retaining the shape.
Good afternoon, everyone. It's my great pleasure to be here today. My name is Mohammed El-Gawadi. I am the interim director for Center for Infrastructure Engineering Studies at Missouri University of Science and Technology. I am a professor also of civil engineering at the same university. I would like to thank my students, Farah, Islam, and Ahmad Ghani, for carrying out the work. So today I'm going to talk about 3D printed environmental friendly concrete. So I'm not going to go through the introduction. We have seen enough today about the introduction, advantage, and so on. So I'm going to skip those. So why alkali activated concrete? Again, we are here on the ACI. Knows about the disadvantage of using Portland cement with the CO2 emissions. So we try to replace the Portland cement with more environmental friendly solutions. So we're looking for alkali activated concrete, which is where we're using a waste material such as fly ash or slag, and then we activate this using alkali solutions. So over here we are going to use the alkali solution that we are using is sodium silicate and sodium hydroxide. So fly ash is a byproduct material. One of the things in Missouri, we are one of the largest, we have one of the largest coal power plant in the state. So we have plenty of fly ash in the state. And we are going to focus, like, per STM 618, we have two different types of class of fly ash, class F and class C. Class F basically is low calcium content versus class C, high calcium content. What we have in Missouri, and which would be the core of this study, is class C. So this study, we're going to, when we look at started looking at the different procedures available in the literature for 3D printing. So one approach is to use continuous mixing. So you basically do the mixing and bumping at the same time, or you can have a continuous preparation of small batches, and then once you prepare the batch, you start pumping. Or you can have mixing at the nozzle head over here. The other one is to use large single batch. So those basically the four methods that we found on the literature for 3D printing. So the objective here from our study here is to prepare a different mixtures that can be used for different procedures. So we are looking for optimizing different mixtures for different procedures. So for example, the first three ones over there would require a very high static yield versus the large one over there, which would require a low static yield for like evolution. So this is just material characterization. So we start looking at the fly ash that we have in the States. So before we start over here, so the sponsor of this project is a mix between Missouri Department of Transportation and Missouri DNR. Those are the environmental arm of the state. So we started actually by collecting fly ash from every single like power plant in the state. So we collected fly ash from 25 locations, and based on those we end up with 7 resources. And today I'm going to present the results for only one supplier. So for this supplier, we have calcium content of about 37%. We did also a lot of characterization. Other characterization is not presented over here. And then we have the sand. So this is the alkali activator. As I mentioned, sodium silicate and sodium hydroxide. The sodium hydroxide is 10 molarity. And then for the sodium silicate, it's about 56% water versus 44 solids. We looked at a lot of mixtures. We did machine learning as well to optimize some of the mixtures, and end up with those 7 mixtures that we are going to focus today. So those 7 mixtures would have different characteristics. So water to fly ash ratio up to 0.4. We have alkali to fly ash ratio about 0.3. And then we have sodium silicate to sodium hydroxide moving from 0.5 to 2. So let's start looking at the open time. So open time is very important for extract. So as we hear today, there is not yet a strict standard for developing 3D printing. So what we use over here as an indication for extractability, we just use a mini slump, and we prepare the mix, and for we prepare different mixtures, and then for the mixture we start to get mini slump until we have 0 slump, and we recorded this time as the extractability time. And then we also run the initial setting time, and then we have some relationships over here. So for example, as we would expect, by increasing the sodium silicate to sodium hydroxide ratio, you would see a drop in the open time and also the initial setting time. For the different mixtures that we selected, we have open time ranging from 3 minutes to 90 minutes. This is slightly lower than the initial setting time from 7 minutes to 170 minutes. The other property that we looked at is the buildability. So for the buildability, that's mean how many layers you can add on top of each other before you see collapse. So this is also related to the cycle time, how many minutes between adding the different layers. So we looked at from 1 minute to 5 minutes, and those were used with the short open time. So for mixtures with short open time, that's mean it would get set very quickly. we use a small cycle time up to 5 minutes. And then for other mixture that has a relatively very long open time, we went actually up to 60 minutes. Some of those maybe seems unrealistic, but we just would like to look at the wide spectrum of the performance of these specimens. For the buildability, we don't have again a standard test. So what we propose over here, we try to look at we have this plastic ring over there, and then we add this is the concrete under investigation here, and then we start to add different steel masses on top of those. So we add the steel mass, different steel plates. So the weight of every steel plate is actually equivalent to the weight of the cement layer over there. So every one of those steel plates represent another layer added on top of the mortar over here. And then we measure the strain. So we have 4 dial gauges to measure the strain, and then we get the average as a strain for this layer of printed concrete. And then based on how, like, what is the toll and how much tolerance for deformation, you can pick, okay, what is how many layers you can add, and then you can link this back to your cycle time. So here's just some results for, like, for different cycle times for 1 minute, 2.5, and 5 minutes. So as you would expect, with increasing the number of stacked load, you get more strain. And again, you would see much lower strain here, for example, with a cycle time of 5 minutes, very high strain here for a very short cycle time. So we, along this line, also we looked at the as I mentioned at the beginning, we look at the different parameters. So we look at the sodium silicate to sodium hydroxide ratio, and relink this, so again, to the cycle time and the strain on the layers. Well, for the yield stress evolution, we would like to also look at an easy to do test. We did also some viscometer testing, but we would like to look at an easy to do test that probably can be used, like, as a quality control later on. So what we did over here, we adapted the penetration test over there. So we look at the potentiometer over there, and we did so we have the specimens, and we did the penetration under just self-weight at different times for the different mixtures. And then we look at, for different rest time, we look at the what we call the static yield stress over here. And we found really a very nice, correlation, very nice linear correlation for the different mixtures. And then would like to see if what we did over there is, can be correlated to more rigorous, testing. So we went to our viscometer. We have viscometer 6 over there. So we did the static yield stress, which again is important for buildability. So if you're not familiar with the reometer over here, it is 2 cylinders, the outer one and the inner one. We have some dimensions over there. The inner one is 50 millimeter, the outer is about 60 millimeter, and then the concrete filled in between, or the mortar filled in between, and then do apply your torque. And then this is what you get for, we did the test up to 25 seconds over here. So we did the test for different resting time. So went up to 20 minutes resting time. And then we did a correlation actually between what we get from the potentiometer and the viscometer over there. And again, we see really a very nice correlation over there with, if you look for R squared here, it's 0.98. And for the other mixtures, actually the lowest R squared that we get is 0.91. So there is really a very strong correlation between the potentiometer and the static yield stress, given the fact that potentiometer is much easier to do and can be used for quality control rather than the viscometer. And then what's really important in the end over here, we have a correlation over here between the cycle time, the static yield stress, and we correlate them through this one. So if you know your cycle time, you can figure out how much requires static yield stress or vice versa. And then next here, based on this, we end up with proposing, like, for, as I mentioned, like we have different mixtures. So we propose, like, if, for example, if you have a continuous mixing, you can look at those 3 mixtures. And if you have like mixing long single batch, you have other mixtures and so on. So based on the characteristics over here, we start to tailor different mixtures for different printing procedures. Once we have done with the fresh properties, extrusibility, buildability, all those stuff, we start looking at the mechanical properties. So for mechanical properties, for each one of those mixtures, we did some concrete cubes. So we have the, for each mixtures, we have two types of specimens. One that is like a single cube, like a monolithic one, cube, and then we also have the layered one over there. And for the layered one, we did test on the X direction and then on the Z direction as well. What we did over here for all the work that we did for the mechanical properties, it's ambient cure, so we didn't use any heat. So we only use ambient temperature for 24 hours and then moisture room for 28 days. Muhammad telling me I have only 2 minutes, so I need to move quickly here. So what we found, let me just jump here, with the different direction, loading direction, you can lose up to 20% in terms of compressor strength, and also in terms of different cycle time, you can lose up to 50% of it. If you have a very long cycle time between these layers, you can lose 50% of your compressor strength. And then we did also pull-off testing. So we have the different layers, and then we just did a pull-off testing to determine the tensile capacity between the layers. And this is the different failure modes that we achieve. So if you have really, as I mentioned, we really went some extremes just to see the full spectrum. So sometimes, if you have really very long, you just get really as cold joint, if you like, and then you get the separation here. We also did slant shear between the different concrete mixtures. And then we end up with, based on all this, we end up with, printing the mixtures. And when we did the printing, we did some of the really well-worked print like mixtures, and also we did some of the specimen that we said that would fail, just to ensure that things would, follow whatever we developed. So as I mentioned, some of those really, you can see some of those, failed, and based on our criteria that we developed, it should fail. And this is the conclusion. I think we don't have time to go through those. I would like, as I mentioned, acknowledge the MoDOT and Missouri Department of Natural Resources, and thank you. Not sure if you have questions.
Thank you very much. There's time for one question. I actually have a question. So, strength-wise, how does this compare to regular concrete?
Well, some of those mixtures actually reach 6,000 psi, 7,000 psi. It all depends. We spent a lot of time on the optimization of the mix itself.
Thank you very much.
Thank you.
Thank you. So I'll put the last. Set of PDHs. Okay, please. Thank you.
Good afternoon, everyone. My name is Mohammad Saeed Zafar, and I am a PhD student at the University of New Mexico, working with Dr. Mariam Hajati. And today I'm going to talk about designing 3D printable eco-concrete by utilizing biodegradable rheology modifiers. So this will be the outline that I will follow throughout this presentation. First, I want to talk about the bio-inspired material. So basically, bio-inspired material can be classified into 4 different families. It could be a material that could be inspired from the recycling process, or how the natural material responds to different in terms of mechanical performance. And there are a lot of 3D printing attempts made by different researchers, starting from the bio-inspired architecture and toward the bio-inspired materials such as clay printing. So if we talk about 3D concrete printing, rheology and green strength, it is very critical to control both of these parameters. And Mosia et al. Suggested a tetrahedral model to discuss how different factors are interdependent on each other, and they place the green strength and rheology right at center, analogous to the oxygen atom in silica tetrahedral. So if we further talk about 3D printing requirements in terms of rheology, there are very contradictory requirements at each phase of printing. Starting from pumpability, we need a material that has a low dynamic yield stress, so that it is pumpable easily. Similarly, in extrusion phase, we need material that has sufficient dynamic yield stress and plastic viscosity, so it doesn't block the nozzle. And right after the material leaves the nozzle on the printing bed, all scenario changes. We need material now that has high static yield stress and high thixotropy, so that it can sustain the load of the layers on top of the bottom layer. So, considering that importance of rheology, viscosity modifying admixtures are widely used rheology modifiers in types of material where rheology is a critical parameter, such as self-compacting concrete and also 3D printing concrete. And the viscosity modifiers are divided into 3 different classifications, starting from natural polymers. Natural polymer is further characterized into 2 classifications: natural starch and also biogums, such as xanthan gum and also cornstarch. The second family is semi-synthetic polymers, and the main member of this family is cellulose ether, such as methyl cellulose and hydroxyl cellulose. And finally, synthetic polymers are there, such as polyvinyl alcohol and polyethylene oxide and others. So in our work, we use all biodegradable rheology modifier, belongs to family of starch, biogums, and cellulose ether, such as xanthan gum, methyl cellulose, and 2 different types of cornstarch. This is the generalized mixed composition of different viscosity modifier. So we use viscosity modifier in different proportion as percentage weight of cement, starting from 0.5, 1, 1.5, and 2%. For the initial testing, we did flowability test and rheology testing. We used Brockfield's rheometer, equipment van shear geometry, and also we use a statistical loop technique to interpret the different parameters such as plastic viscosity, dynamic yield stress, and static yield stress. So in the initial testing, we use all these modifiers are individual in the mix with cement, sand, and just water. So the response of cornstarch, that we use 2 different types of cornstarch brands. One is the capsule and other is Ultratex. So the cornstarch with capsule brand, the water demand was quite low and flowability was significantly improved with adding this. But the main rheological requirement, that is plastic viscosity and dynamic yield stress, was quite low. That it doesn't satisfy the requirement to be 3D printable. Similarly, the second cornstarch classification, in this case, water demand was quite higher and also flowability was reduced, and we experienced the same problem with plastic viscosity and dynamic yield stress, but static yield stress was improved significantly in this case. And also methyl cellulose, although all the rheological requirements were in the printability range, but when we added methyl cellulose content more than 1% weight of cement, the mix was very viscous that it was not easy to work with that mix, and it was not easy to print that mix. Finally, the xanthan gum, the water demand was quite higher in case of xanthan gum. The static yield stress was improved, but again the plastic viscosity and dynamic yield stress was very low. So considering this problem, when we tried these material individually in the 3D printed mix, although some of the properties were improved, but on the other hand, we have to compromise some of the parameters. So to eliminate that process, we decided to use these mixer in different combinations. But how to optimize, how do we know that this mix will be the optimized combination? So to do that manually, there will be a lot of experimental effort. So to eliminate that effort, we use a design of experiment technique, response surface methodology, and In responsive field methodology, we use central composite design to eliminate that experimental effort. So as an initial input, we use design expert software, and total 47 experimentation was done to collect the preliminary data that are three responses: plastic viscosity, dynamic stress, and static yield stress. So if we talk about the interaction of three different material in the system, there was different behaviors that we can see in this. That methyl cellulose has considerable effect on plastic viscosity and dynamic yield stress when we keep the cornstarch and xanthan content as a constant. But if we talk about the static yield stress, xanthan gum has significant effect on the rise of the static yield stress in the system, and we can see this here in this graph too. Okay, so after optimization through responsive methodology, the optimization suggests us around 100 different optimized mixes. We selected 4 different mixes for preliminary printability evaluation based on the value of static yield stress, plastic viscosity, and dynamic yield stress. So the first mix that contained 2% of all 3 factors A, B, and C. For the extrudability evaluation, we printed a filament with different printing speeds, starting from 15 millimeter per second to 35 millimeter per second, to get a optimized printing speed that is giving us a good extrudability. And the optimized printing speed in this case was 15 millimeter per second, and we get a good extrudability in terms of dimension consistency, conformity, and also the surface quality, as you can see, is very good. For the buildability evaluation, we printed a wall, and we measured the total height of wall, and also at 2 different intervals, like after printing 10 layers and after printing 20 layers. And this mix was buildable up to 20 different layers. And this was single layered wall with 20 millimeter dimension of the filament. Similarly, for mix 2, that has different content of both the factor A, B, and C. Again, the printing speed for this case was 15 millimeter per second, and we get a good dimension consistency and conformity in this mix too. And again, in terms of buildability and shape retention, you can see the shape retention is quite good in this case. And the buildability, this mix was collapsed after 15 years. The reason behind this is the static yield stress of this mix was comparatively low as compared to other 4 mixes, so this mix collapsed early. About mix 3, again the optimized printing speed in this case was 20 millimeter per second. And again, you can see the quality of extrudability in terms of dimension consistency. That design dimension was 30 millimeter, and we were able to achieve that exact dimension with printing speed of 20 millimeter per second. For the buildability, again, this mix was printable up to height up to 21 layers, and it collapsed after printing 21st layer. Finally, the mix 4, we try a different xanthan gum type in this case, but that leads to rise the water requirement, and you can see surface cracks in this case because of high water demand of the mix. But the mix has good extrudability in terms of dimension consistency and conformity. The only defect in terms of extrudability was the surface quality. That was not good. You can see a lot of surface cracks in this case. Again, because of high static yield stress and thixotropy, this mix was buildable up to 23 layers. But you can see the surface quality here is also not good there. We can see a lot of cracks. And shape retention was quite good in this case too. To summarize, we get 4 different optimized mixes. Out of 4, the 3 satisfy all the printability criteria, starting from extrudability, buildability, and shape retention. And extrusion speed, the optimized extrusion speed was same for all the mixes. And also printing speed was same for all mixes except the mix 2, that the optimized printing speed was 20 millimeter per second. To conclude, we observed that the individual inclusion of these admixtures was not effective, and we saw a lot of negative impacts on the rheological parameters. And we applied the response surface methodology that is a very effective tool to get the optimized mixes. And when we include the viscosity modifier in the binary and ternary optimized mixes, we get very optimized rheological parameters such as plastic viscosity, dynamic yield stress, and static yield stress. So the best mixes in terms of printability was mix 1 and 2. The mix 1 contained 2% of cornstarch, 2% of methyl cellulose, and also 2% of xanthan gum. Similarly, the mix containing 2% of methyl cellulose and xanthan gum displayed better printability in all the criteria. Finally, it can be concluded that all these viscosity modifier, cornstarch, xanthan gum, and methyl cellulose are quite effective biodegradable mixes. And the ranges of the rheological parameter we found was 5 to 16 pascal second for plastic viscosity, 200 to 1100 pascal for dynamic yield stress, and 1300 to 4500 pascal for static yield stress. We are currently working on the next phases of this project, that is evaluating the grain strength optimized mixes by two different approaches, direct shear stress and unconfined compressive strength test. And also, it is very important to evaluate the hydration kinetics when you are using VMA in the mix. So we are doing calorimetry for that. And finally, we want to check what is the effect of adding viscosity modifier on mechanical performance in terms of compressive strength. I want to thank finally the main sponsor of this project, Transit, and other vendors to supply the material. Thank you very much for your attention.
Thank you for the time. So we have time for questions. Okay, so you mentioned you will be looking for the strength. That was, but do you have any preliminary results on the strength right now?
Yeah, we tried one of the mixture methyl cellulose, but that was ECC mixes. And we saw a little decline in the strength, but it was still not very significant as compared to the mixes without methyl cellulose. And we're expecting same for the other viscosity modifiers too.
Thank you very much. Thank you very much, everyone, for attending, and we hope to see you more and more. And I just would like to say that this three-part session was sponsored by the 3D Printing Committee 564. So we have, within that committee, we have three different subcommittees looking at the materials, looking at the design aspects. So the design, structural design committee is working on design guidelines, and I forgot the third. The report, the emerging report, emerging technology report, which is talking about the emerging technology, and we would love to have helping hands. Thank you very much again, and see you soon. Thank you.